All right. All right. So this is the FFTX tutorial. FFTX, I'm going to give a brief introduction to what FFTX is. I'm Phil Claw, the project lead, and we have a team that's spread over 3 sites, Lawrence Berkeley Lab, Carnegie Mellon University, and SpiralGen, which is a small company in Pittsburgh. So let me start. So my job is to kind of provide some context. So I think part of the context here is you need to have a little bit of an understanding of how fast Fourier transforms work. And for the way they work is that for a radix n, so you want to do a discrete Fourier transform of size n, of an input of size n. What that is mathematically is multiplication by an n by n matrix, which is order n squared operations if you just do it as multiplication by an n by n matrix. To make them go fast though, you decompose transforms of radix n into smaller transforms. So how do you do that? Well, there are basically 2 sets of tricks. One of them is Cooley-Tukey. That is, if your radix is actually the product of 2 smaller integers, you can transform, you can express the transform of radix n as n1 transforms of radix n2 plus n2 transforms of radix n1 plus order n flops. So that's one way of expressing big transform as smaller transforms. The second way is if you have, so there are 2 flavors of this algorithm. One is for prime numbers and the other is really for any n. So for Rader or Bluestein, you can express a discrete Fourier transform as a periodic convolution, which can be then expressed in terms of a discrete Fourier transform of any size n prime as long as it's greater than 2n minus 1. So then you can choose n prime to be highly composite so that you can apply Cooley-Tukey. So the heavy lift here is going from a discrete Fourier transform to a periodic convolution. The expressing that in terms of a discrete Fourier transform of any sufficiently large size is an old story. That's something that's familiar to computational physicists as the Hockney algorithm. So you can take these 2 ways of transforming Fourier transforms of size n and compose them in various ways and obtain order log n transformations using either Cooley-Tukey or Rader Bluestein to get O of n Fourier transforms of size order 1, which can be computed directly. So when the dust settles, you can get a Fourier transform rather than in order n squared flops, in order n log n flops. So what's the problem? So this sounds like the question is answered. The problem is that there isn't one such transform. There are a large number of order n log n decompositions of size and size n discrete Fourier transforms. Then when you add multi-dimensions, then you add symmetries like real inputs and outputs, sine and cosine transforms. For each one of those, there's going to be this large family of decompositions that will get you order n log n operations. The second thing is that no matter what you're doing in this space of algorithms, you end up with low arithmetic intensities. So for a classic radix 2 complex to complex transform, it's about 0.3 log base 2 of n is the arithmetic intensity. Improving the performance will also involve reducing the amount of data motion wherever possible. On modern GPU-based architectures, these 2 considerations lead to complicated algorithms and implementations whose structure depends on the architecture and the type of the transform, including its size. So it's that last statement that really complicates matters in a serious way. So what is our approach to dealing with these problems? The fact that we're in a complicated algorithm space, and the fact that we need to control data motion. So there are two pieces to the puzzle. One is a cross-cutting infrastructure that obtaining high-performance machine-generated code. And the infrastructure is based on Spiral, an open source symbolic analysis and code generation toolchain developed by CMU and SpiralGen that takes a high-level specification of an FFT-based algorithm and automatically generates code for HIP, CUDA, CPUs, and eventually SYCL OpenCL. So that means we'll cover pretty much all the high-performance architectures in DOE. In addition to that, so this is a rather exotic tool chain. However, what we present to users are C++ APIs that connect to Spiral code generation. There's performance engineering that has to be done. We're in a complicated algorithm space. The good news is that Spiral abstracts things in a way that allows us to change how we do performance engineering by modifying how Spiral does its business. And so there's a large lever arm there. We're not optimizing every transform one at a time, but we're extracting a set of rules that will give us uniformly high performance. And then what you actually see is good user APIs and workflows. So I'll show you my next slide. I'll show you what that means. Now, in addition, so in doing the code generation for any FFT-based algorithm, part of what we're trying to do is control data motion. But in addition to that, there's another opportunity here for controlling data motion that we are taking in this project, which is to reduce data motion by integrating more of the algorithms involving FFTs into the code generation process. So if you look at things like, say, periodic convolution or free space convolution, and view that as a whole algorithm that has FFTs embedded in it, what you find is that taking that larger chunk of the algorithm and trying to optimize its data motion, you end up with an overall data motion that has less data motion and therefore better roofline performance than ones for which data are written to or read from a black box FFTs. Now, this is very problem dependent, and this is really a co-design activity. We have 3 co-design collaborations: XFEL, WarpX, and NWChemX, where we're attempting to do this. Now, I'm going to show you, just to give you a sense of what FFTX presents to the users. What it presents is a library API. So what I've done is I've written a little fragment, a little piece of code. So this is a user FFT. So so this is a function that might appear in your application, in which you pass in a pointer to complex of doubles. As input, you pass in a pointer that's of complex of doubles, that's the output, and you pass in, and let's assume we're doing a cubic FFT just to keep things simple, so that you have something of size nx and y and z, of size nx. Now I missed something here. This should be nx, nx, nx. So we define the size of the problem, both in terms of a point and then a box, which is given by 2 corners. The 2 steps that you have to do are, one is to create an alias between user data and FFTX data. So we have FFTX 3-dimensional arrays, and this is the constructor that creates that alias, or view, I guess is the modern terminology, between the input data and the FFTX data object. Similarly for the output. Now, once you have that view of the user data coming in, what does actually calling an FFTX transform look like? Well, we have a class MDDFT 3-dimension, which is multi-dimensional discrete Fourier transforms in 3 dimensions, and we create an object of that class with this size 3D, so this box going 1 to nx. And what that does is it accesses the forward transform, which is on the order of 1,000 lines of code in CUDA or C or whatever. And then to execute the transform, forward FFT is a C++ class. It has a member function transform, and you apply transform to input FFT, output FFT, that calls the forward transform. And now you're done. That has computed the 3D Fourier transform of the input data, put it in the output data. Since these are views into user data, that means you have put things into the output data, no copying. Now, what's the catch? The catch at the moment is the current limitation of FFTX deployment is that a list of sizes for a given type of transform must be specified at the time the library is built, with access to pre-built transforms provided at link time through a dynamically linked library. However, regardless of how this changes, we are going to do something that is more general, that doesn't require you to specify what sizes you're going to want at build time, at the library build time. As we go forward, it's still this API you're going to see. So what's the rest of the tutorial look like? Patrick Broderick from SpiralGen will give the heart of the tutorial as a tutorial, which is how to install and use FFTX FFTs for a single processor device. Peter McCorkadale will talk about the other part of our project, which is what integrated algorithm co-design looks like. And he'll do it by walking you through what we are doing with the XFEL team. Tse-Meng Lo will talk about our multiple different ways in which we're supporting distributed FFTs. And then Franchetti at the end will talk about how we eliminate the fixed list library, spiral code generation, and real-time compilation. So that's it. So let me move on and turn it over to Patrick.
Okay, thanks, Phil. Let me just get my screen sharing going here, and we should be good. So, can you see my slides?
Yes.
Okay. So I'm going to talk about obtaining and installing Spiral and FFTX. FFTX depends on Spiral for code generation. So we need to download and build Spiral first, and then we will be able to build FFTX and the libraries. And once the libraries are built, we'll talk briefly about how you would access and use them. And you got a very high-level overview of that just a moment ago from Phil. All of the code is available on GitHub in GitHub repositories, and the repositories are all listed here on the left. Just briefly, there's a few prerequisites required in order to build and install all the code. A lot of it's pretty bog standard stuff: compiler, make tools if you're working on Linux, Visual Studio if you're working on Windows, and if you're on a Mac, you need Mac OS 10.14 or later, or you need the Xcode and Xcode command line utilities. You also need CMake. We use CMake in order to to create our build system and to go off of that. And Python is also used in generating the library code and building. Along with each of our repositories, we have a README, and there are some fairly detailed instructions in the README, including all of the prerequisites that I've just mentioned. So if you're going to try and build this, obviously you want to take a look at the README and be aware of what's there and try to follow that. Each of our repositories in general has a main or a master branch, and that's obviously the one we encourage people to download and use. We have a develop branch, which typically we promote what we believe is working code to the develop branch. And it's there for other team members to make sure that they can kick the tires on it and that it all looks good. And while it's generally the latest, greatest, it hasn't yet been fully certified and released. So if you do ever go to the develop branch to get something that's the latest, greatest, just be aware that you know, there's sort of, your mileage may vary in case it's not all fully functional. But everything we're going to do today is going to go from the main or the master branches. All right, so you know, in order to build Spiral, we're going to end up making a directory and you know, pulling down the software and actually building it. And I'm going to actually try and demo that in, you know, here in real time without the aid of a safety net. So typically you're going to want some directory where you're going to do this. And, you know, my simple example is just create a work directory off your home directory, wherever that is. Once you've done that, we're going to do, you know, git clone, and that will pull down the software. Now I've gone into the directory, and you notice I'm setting a Spiral home. Spiral home environment variable is going to be used within FFTX. We don't need to set this variable in order to build Spiral, but we're going to need it later. So I'm going to set it now anyway. The second thing that I'm going to do here really is pull down 3 additional repos, and these are Spiral package, and they're Spiral package FFTX, SIMT, and MPI. For what we're going to do today, we don't really need MPI, but MPI is going to be referenced and needed later once we kind of start talking about distributed FFTs. One of the things to note, and I did highlight that here, is that these Spiral packages need to be pulled into a directory called namespaces packages, which is under the Spiral software top level directory. And each of the package names needs to be put in a directory with just the last piece of the name. That's so when Spiral is looking for these extensions that are in the packages, it looks for them just by the last piece of the name. So I'm pulling it down into a folder called FFTX or SIMT. And if I do that right now, you can see that I've gotten FFTX, MPI, and SIMT. So once I have all of this down, I can actually go ahead and go back to the top level, run CMake, and then fire off a make install to build Spiral itself. And this builds pretty quickly. It's only going to take a minute or so. Once it's built, I will be ready to be. I can now go ahead to the next phase of the install, which is go ahead and get the FFTX software and get ready to build it. And as we've seen, so Spiral has complete. The installation of that is there. For FFTX itself, again, I'm just getting the repo, and I'm going to start that off. So I pull down the repo. I'm setting FFTX home variable because I'll use that later once I go to try and connect to the libraries that eventually get built. Let me just go back to the slides now for a minute and we'll talk about it. FFTX home really ultimately wants to point where you install the libraries, the header files, the makefile utilities, etc., that we will be installing as part of the release. You can see that I go to the source library directory, and from there I'm running a build libcode shell script. This shell script is the one that's actually marshaling Spiral, the code generator, in order to kick off Spiral and create the source files that are going to get compiled. This shell script takes an argument And the argument is one of CPU for building code for a CPU, or either CUDA or HIP if I'm going to also build code for a GPU, CUDA or HIP GPU. This process takes a while, so I've got it running in the background. It's probably going to take, on the order of 20 minutes to half an hour to create all of the library code for FFTX for the fixed sizes that we're going to work with here right today. And I'm only going to build it for CPU. Clearly, if you're pulling it to a laptop or a local machine and you don't have a GPU, well, you're not going to be successful if you try to do that. But for our purposes today, we're just going to stick with the CPU. And this will probably run longer than my section of the talk, but if we have a little bit of time at the end, I will try and come back to it and show you that we've built the code, built the libraries, and we can, possibly link to a library afterwards in a small example. I'm going to issue these commands to it at the end so that they run when this is all done. You notice here that I'm setting FFTX home. We will need that when we go on later to try and link against FFTX. So what libraries are we building? We're building a total of 9 libraries right now. The multidimensional DFT, the inverse for that, packed real DFT, so that gives you some, real to complex, complex to real. And then we also have some batch 1D DFTs as well. We do have an additional repo, which I will mention in a couple of minutes coming later, where we have a couple of small examples that illustrate how we link against these libraries and how you as a user could look at some of the artifacts in that repo for your own use. You can look at the CMake file if you want to use CMake later on to link our libraries to your code. Okay. As we've mentioned, we're building libraries with a set of fixed sizes today. So if we have sizes pre-built that you can use, that's great, you're ready to go. But if we don't have the size pre-built and you would like to try using our libraries, what would you have to do in order to get that done? And that's what I want to cover here. So the code generated by Spiral is optimized based on the problem size. So each unique size needs to have the code generated and then compiled. Now we have a set of sizes. They're in a couple of files, which I'm going to cover here in a second. But if you want to add additional sizes, it'll be either of these 2 files, i.e. cube sizes, which defines the sizes we're going to build for all the 3D transforms, or DFT batch sizes, which lists out the sizes for the 1D transforms. The format of these files is pretty simple. Anything following a hash is regarded as a command and is ignored. White space lines are ignored also. So the real meat of this file is just a set of Z-cube assignments, which just gives the sizes we're going to build. Most of the sizes in the library are cubes, but not all. So it's not required that we have a cube, an exact cube. Some of the sizes are non-cubic. But if you want to add a size, you would just simply go into this file, edit it, add an additional line with the Z-cube equal to the size you want. The DFT batch sizes is very similar. It's set up in the same way, only we're going to define 2 things in this file. One is the number of batches, and the second part is the size of the 1D transform. So again, there's a number of examples here showing 1 and 4 for sizes 100, 120. Once you've edited these files, all you would need to do is go back and rerun build lib code to recreate all of the source files. And once the source files are all created, you can go back to the build directory and do a make install. I do have a note that, as of right now, it's kind of a complete regeneration. We can make that a little bit smarter so that, it's a little easier to add 1 or 2 sizes and that you don't have to go recreate everything again. But currently, that's a small limitation. Using CMake. As I mentioned, Spiral and FFTX are all built with CMake. CMake definitely helps simplify the building in a portable cross-platform manner, and so we use CMake and we rely on that. We have as I alluded to a moment ago, we have another small repo called FFTX demo extern app, which is just a small external from FFTX repo. And the purpose there is we just put in there a couple of small, pretty simple programs that will link against the libraries we created. And they're just, they're meant as, quick, fairly easy, quick programs to show some of the things we can do with the libraries. FFTX demo is built with CMake, and that CMake file, if you were going to use CMake and link your application to FFTX, you can certainly probably pick up a lot of what you need to do that right out of the CMake file we have in that FFTX demo app. When we're using CMake to link with FFTX, we're expecting FFTX home environment variable to be set, and that's how we find where the FFTX is installed and link against that. What else do you need to know if you want to link to our stuff? So we have, with FFTX, we have FFTX CMakes functions, which contains several utility functions to either help us build FFTX, and provides also a couple of externally callable ones to help you get a list of the path names and library names to include in your project. And there's 2 principal ones, which I'm going to call out here. One is FFTX find libraries, which will find the library names, the paths, and the include path names that are needed. And that exposes a couple of CMake variables, which are listed here. So it's FFTX lib include paths, lib names, lib library path. And if you need access to those individual variables, you can call that function. However, we also have another function called FFTX add includes libs to target. This function just simply takes your target, and the target would be perhaps the name of an executable that you want to build. So in my example down here on this page, I'm adding, I'm assuming you have some familiarity with CMake, but CMake lets you add an executable, which is just given the generic $project name here. It depends on project.cpp, and that's going to be one of my targets. And then when I want to associate the include file path names and the libraries, etc., I just call that FFTX add includes and libraries to my target. And that's pretty much what I need there. You can also use make. Make is probably something maybe even more people are familiar with than CMake. Make can do it, but you've got to specify all of the variables and libraries, etc. The other issue with Make is it's really not as portable unless you do, unless you kind of work at it a bit more. One of the things we have certainly found is that CMake gives us a lot of flexibility when moving from one platform to another. One other thing that I'm going to mention is that, in addition to the high-level C++ API, should you need to, you can actually get at, at some of the things in the library at a slightly lower level. For this tutorial, and I've talked about only generating a CPU code. We're only going to generate CPU code because perhaps many laptops don't even have a GPU. But generating GPU code is indeed possible, and the code for both the CPU and for the GPU is put into the same library. And of course, typically we'll of course only generate either CUDA code or HIP code. You wouldn't expect to have both included in the same library. Over here on the right-hand side, I note the library names, and then along with each library, there's a public header file that you can include in order to gain access to the functions and information within that library. One of the functions, or really two that I'm calling out here, is the get library mode and the set library mode function. That's not going to be very important when you only generate CPU code and there's nothing else in the library. But if you have both CPU and GPU code in the library, you need to know which mode you're operating in. Because if you're going to call code and execute something on the GPU, you need to make sure that your data, input and output data, is allocated and written to the GPU and then copied back to the CPU for the output later to to work with and analyze it. Anyway, by convention, when we create the library, if GPU code is added, then the default library mode is the GPU, and that'll be either CUDA or HIP. Otherwise, it's CPU. If you want to write an example or run a program that uses both GPU and CPU code, or different, both versions of the transform, you need to set the library mode appropriately when you want to call CPU versus GPU. So the external demo app, which I mentioned a moment ago, here's the link for it. This application currently contains 3 small test programs. A small test that will exercise the DFT 1D libraries. There's a Poisson test program, which is for CPU only. And then there's a transform lib test program, which will exercise the MD DFT library, and it just exercises all entries in that, but it's doing it for CUDA. It doesn't do it for CPU. And we also have a CMake list, which I mentioned. I showed a couple of extracts from it, and it's a good reference point if you need to link your application against our libraries using CMake. One last thing I'm going to point out is that very recently we have had SPAC definitions for all of the packages merged into, they're currently just in the develop branch of SPAC. But if anybody is trying to use SPAC for their work or development work, you would be able to deploy Spiral and FFTX using SPAC, again from the develop branch for now, but that will obviously come in a future release. So that's where I'm at. I'm just bringing back up my terminal window, and It is still running. It's actually got just a little bit more to go, but it's generating the 1D DFTs. So pretty soon it will get on to running CMake and make install. And if we have time at the end, I'll come back for a couple of minutes and we'll look at that again. But otherwise, that's what I have for now. So Phil, I'm going to turn it back to you.
All right, good. I feel like we ought to, for this particular case, we ought to stop and see if anyone has a question or two. We have reserved some time, 20 minutes at the end for questions if you want to wait until then. All right, so I think next up is Peter McCorkadale. So Peter, go ahead.
Okay, thanks, Phil. Not sure my phone is ringing right now. It's a number I don't recognize. Okay. Okay, I'm going to talk about integrated algorithms in FFTX, in particular a case study with EXA-FEL, which is the ECP project for data analytics at the exascale for free electron lasers. Okay, so Phil mentioned something about integrated algorithms briefly in his initial talk, and so these are, for our purposes, algorithms that combine FFTs with other operators, such as linear operators. Now, the spiral symbolic analysis and code generation system handles more than just FFTs, from simple operations like just padding and pruning arrays, diagonal multiplication, more complicated things like tensor contractions. So spiral can do that too. And of course, spectral methods such as convolutions, fast Poisson solvers consist algorithmically of compositions of FFTs with linear operators. So we can have spiral generate the most efficient combined algorithms. That's the basic idea. And the advantage, well, the obvious advantage is that there's less data motion than having separate function calls. And as a result, we get better performance. And I'll show the flowchart of the Spinifel code for single particle imaging. This is the MTIP algorithm. And here's the main flowchart on the top right. And here's a subroutine of it on the bottom right. This is actually an inverse non-uniform fast Fourier transform. And okay, so the part on the left is called phasing in the MTIP algorithm. And the inner loop in phasing, which I've shown in yellow here, consists of a forward 3D FFT of the density, and then keeping the same phase of the in Fourier space, but changing the amplitude, and then doing inverse 3D FFT. So that's phasing, which is similar in structure to a periodic convolution. And in the in red here, this is the inner loop of the merging step in the MTIP algorithm, which takes the form of free space convolution, where you have an array, a three-dimensional array, use zero pad, all three dimensions to double their length, do a forward 3D FFT, multiply by a symbol array, inverse 3D FFT, and then prune by half in every dimension. And we found that we learned from the XFL people that the execution time of Spinifel is dominated by phasing and merging, as shown in this graph here. Phasing in yellow, merging in red take up most of the time, and the phasing time is dominated by uniform FFTs, as I showed in the previous slide with the inner loop. And the merging here, the biggest part, consists of non-uniform FFTs, as I said before, but in the non-uniform FFTs, the time is dominated by the free space convolution that I showed in the previous slide. And most of that is in uniform FFTs. Okay, so So if you do free space convolution using a 3D FFT library routine as a black box, you have the three basic computational steps. You call the forward 3D FFT on a zero padded input array, multiply by the symbol, and call the inverse 3D FFT and prune the output back to the original size. Now, internally, a 3D FFT of size 2m by 2m by 2m will be performed by the library routine using three passes, one pass in each dimension, and in each pass you do a lot of 1D FFTs of length 2m, and in each pass the library routine will read and write all the data consisting of 2m times 2m times 2m scalars, so 8m cubed scalars. And as for the use cases within MTIP, so each convolution is computed on a single device on 3D grids of length around 100. And this convolution is memory bound, so the roofline limit is determined by the amount of data moved, and therefore we want to increase performance. The way to do that is the simplest way to do this to reduce data movement. Now, we can reduce the data motion as well as the number of arithmetic operations by not padding all three dimensions at once. So start by padding just the x dimension and do the 1D FFTs in the x dimension, pad in the y dimension, do the 1D FFTs in the y dimension, and then the same thing in the z dimension, and then multiply the symbol array, and then do the inverse 3D FFTs, sorry, one dimension at a time, reversing the process that you did in the forward dimension, so where you, in this case, you prune one dimension at a time, and you end up with the output the same size as the input. And there's a way to reduce data motion even more, which is to combine the parts that I've shown shaded in blue here into an integrated algorithm consisting of the last pass of the forward 3D FFT with multiplication by the symbol array and the first pass of the inverse 3D FFT. So this part in blue, it reads in 4m cubed scalars from the second pass of the 3D FFT and writes out 4m cubed scalars as input to the second pass of the inverse 3D transform. So in summary, when we compare free space convolution using 3D FFT library routine as a black box with the dimension by dimension padding and pruning and the integrated algorithm, we save some floating point operations. But more important is that the number of reads and writes is reduced by a little more than a factor of 4. So yeah, so the Spinifel code is written in Python. We were showing examples with C++ earlier, but Spinifel is written in Python, and so we had to come up with a Python interface. And now here on the left is what the convolution kernel looks like as implemented in Python in Spinifel code, with inputs ugrid and fugrid_conv and the output ugrid_conv out. And yeah, as you can see, it calls functions in the CuPy library. It copies ugrid to ugrid UPS, which has all the dimensions doubled and padded with zeros, and does a forward 3D FFT of it. That's FFTN, and then multiplies pointwise by fugrid_conv and does an inverse 3D FFT IFFTN calling CuPy routine, and finally prunes back to an array of size m by m by m. On the right is the function called our FFTX version that implements the same kernel, and you can just make this one replacement in Spinifel. You don't need to make any other changes to Spinifel in order to call FFTX. Now the other kernel is the phasing step, and it is shown here on the left in the original Python in Spinifel with inputs row and amplitudes. It does a forward 3D FFT to give row hat, and then it extracts the phases of row hat and sets row hat mod to give it sets row hat mod to an input amplitude times the phases except at the point 0, 0, 0. That's why we have this amp mask here, and then and then it does an inverse FFT, this IFFTN here of the result, and takes the real part of that. And on the right, again, the function call to our FFTX implementation can also be put in as replacement in SpinFL with no other changes required. So in our testing, we were given a recommended grid length of 81. So we were able to speed up the phasing step by a factor of 30, as shown by the numbers here. This is running on Cori at NERSC. I do not have timing comparisons for the free space convolution kernel because the implementation of that is not quite finished all the required testing. Now, the way we worked together was all the SpinFL code was by the XFBL team. I communicated with them about it and did the testing with and without FFTX, assessed performance, documented, communicated with the SpiralGen and CMU people who are Mike Feinrich at SpiralGen, who built the Python interface with FFTX, and the software engineering of integrated algorithms in Spiral, which is, as you know, FFTX's code generation backend. And Franchetti at CMU took care of the lower level details of FFTX and Spiral. And what we plan to do next is first organize the Python to FFTX interface in the form of a library with a fixed set of problem sizes and an API to access them. And we plan to couple our uniform FFTs from FFTX to the Flatiron Institute's non-uniform FFT packages, which are used as SpinFL for the merging and slicing phases. And of course, do some more performance engineering and get this all working on multiple platforms, including both NVIDIA and AMD GPUs. So far, we've only run this on Cori, which has NVIDIA GPUs. And the XFL team has been working with OLCF to get their code to work at Crusher, but there have been some stumbling blocks with that. But FFTX itself has been tested and works in Crusher as well as on Cori and CPU platforms. Okay, I see some questions in the chat. Okay, it looks like they've been answered.
All right. This, by the way, is an example of when you get into an application, suddenly requirements appear that you weren't expecting, and one of them was adding Python support. But we've fortunately, this is something that the SpiralGen team has been doing has some experience with from other funding they've had, and so we were able to respond to that requirement. Any questions other than the ones that Ramesh and Brian have been discussing in the chat window? Okay, so let's move on then. So I guess the next up is Semeng. So do you want to share your screen?
Right, can everybody see my screen and hear me?
Yes, yes.
Right. So I'm going to cover FFTX, the different approaches in using FFTX to do distributed FFTs, right? And given this is an ECP, we know that distributed FFTs are part of many applications. And when I say part, they really usually form a single steps out of multiple steps. So here, what I have on this screen is essentially a plane wave applications. And you see that there are many steps, of which the 3D FFT, where you actually have to do distributed communications to compute a large 3D FFTs. That's where this is the domain that we are looking at. Now, to use FFTX, there are actually multiple ways to tackle the distributed problem. So here I've listed out 3 different ways in which you can use FFTX to solve your distributed 3D FFT problem. So option 1 is we have provided a computation of FFT on the local device, whether it's CPU, CUDA, or heap. we now give you the capability to use the pre-built library to actually replace the local FFT in your existing framework for FFTX. So instead of calling, say, FFTW, if you're on the CPU, you can replace that FFT with the equivalent cost in FFTX. And that we've been describing it for the first half of this talk. Right. The second option is actually using the FFTX distributed interface. And within this interface, I will spend more time on it, but the main idea is you describe the input, output, layout, the number of nodes that, and how you would like to parallelize the data. Spiral would generate the necessary local and distributed code so that the entire 3D FFT is implemented without you having to worry about, oh, this part I have to handle myself, this I have to do the MPI myself, and so on and so forth. So that's a second option that I will go into further details. And the last option is to use an existing distributed framework such as Hefty, right? And I will talk a little bit about how we have integrated, or we have started work on integrating FFTX capabilities into Hefty. So the second option, which is the one that is less described so far, is using the distributed FFTX API. Now, what you see on the screen here is on the left, you have a piece of code that is using the FFTX distributed API. The text in black are what you would have to do to describe your local 3D FFT. So in this case, NX, NY, and Z, they are all set to 32. Ignoring the text in orange, you define the size of the data set, you define the multi-dimension DFT, and the text in black essentially are what you would write if you want to do a local 3D FFT of 32 cube. Now, to make this a distributed piece of code, what you have to include as part of the description is really how many nodes you have. So you need to define your compute grid. In this case, we define a 2D grid of 2 processors in each dimension. So a total of 4 processors that's given by this line of code here. And then beyond the number of nodes that and how they're organized, you need to also define how the data on the input and output needs to be. So here we are saying that we define a incoming distribution for a 3D FFT, 3-dimensional data cube, where the first dimension is not distributed, the second dimension is distributed along the X dimension of the grid, and the last dimension of the data cube is distributed on the second dimension of the processing grid, right? And we do the same for the output distribution, we define them accordingly. Now, these are the 3 pieces of information that you need to provide to FFTX. And then when you declare the arrays for the input and output, instead of declaring a local array, if you include the prefix of D underscore, then that defines a distributed array with a particular distribution. So you define a distributed array with the distribution that you have defined previously for both the inputs and outputs. And then most of the code that remains is the same as what you would have to write for FFTX if it was a local piece of code. So a lot of effort we've put into define the API is to keep the distributed API as similar as possible to the local CPU or GPU code that you have to write as well. So it makes it easy to first write your code locally, test it out, make sure it works, and then push it onto the distributed device subsequently. And as we go along with this project, we will be increasing support for more data distribution, more layout combination, and as part of our integrated algorithms approach, we'll be also introducing new capabilities within the FFTX API. So what are some of these new capabilities, right? One of the things as part of our work with NWChem-X is to introduce the notion of embedding the FFT within a larger data cube. As you have heard from Phil right at the beginning, when we look at the integrated algorithms, there are a lot of opportunities where we can exploit zero elements to avoid doing excessive communication. And this is one instance where the actual data is much smaller than the overall data cube itself. So if you had to do a 3D FFT on the whole thing, we could have embedded the non-zero elements into a sea of zeros and then do a large 3D FFT. However, if we can exploit the fact that there are many zeros, which means we don't need to communicate them and we don't need to compute the 3D FFT for them, then what you end up with is a 5-factor less amount of data that needs to be computed. And then there's also some savings in terms of the number of flops that actually have to be performed. So embedding something into a largest embedding is one of such examples when we work with the integrated algorithm and are introducing into the distributed FFTX API. So two of the things that we are looking at right now, number one is the distributed prune DFT. And here, what we are doing is we are exploiting the locations of the known locations of all the zeros. This allows us to avoid sending data that is completely zero. So we know there are going to be zeros, we avoid doing that, and that reduces the amount of communication and data transfer that you actually need to perform. The second thing is that in working with the integrated algorithms, what we've realized is that very often many applications have their own custom data layout and data distribution that may not be strictly block cyclic distribution. So what we are working currently is to allow applications and frameworks that require distributed FFT to actually define custom data layouts. And when you define this custom data layout through access function, Spiral will generate code that will use this accessor function to actually figure out what's the data layout, how much FFT data is on each different node, and then build a custom distribution that computes the DFT with the custom layout. So this is something that's ongoing, and we are actively working on this right now. Right. So to describe what does that prune DFT look like? Well, basically what you need to do is to define where the non-zero elements are, and then embed the non-zero elements into a larger data cube so that we know the actual size of it. And then through this interface, the information of where the non-zeros are distributed are passed to Spiral, and then Spiral will generate appropriate code. And to support for custom distributions, what you need to do is define how many FFTs do you have per node, which FFT tensors are assigned to which node, and then where can these global tensors be located in the local memory. So these are the APIs. The API has been fixed. We are now working on the back end to actually use these functions to actually generate the appropriate distributed FFT code using custom data distribution. This allows applications that already have their own data distribution, own distributed framework, but to have specialized data layout to also leverage FFTX and Spiral to have good 3D FFT, good distributed 3D FFT, right? The last option that I will talk about is our efforts in integrating with an existing framework such as Hefty. Now, Hefty is a distributed framework for doing distributed FFTs, and how it works is it does all the necessary communication frameworks, but for the local computation, it relies on having a backend that has been defined and linked to Hefty itself. So what we have done is to build an FFTX backend and to integrate the FFTX backend into the build system for FT. Currently, what this does is that it allows, instead of calling FFTW or cuFFT for the local FFT, it calls FFTX for the local FFT. This packaging of FFTX within Hefty currently is a standalone fork of the Hefty distribution, and as the FFTX local computation matures, the FFTX library matures, and then what we would then re-engage the Hefty folks to actually push FFTX into our official backend for Hefty. And that's the summary of our 3 approaches. Are there any questions?
All right, so why don't we move on then to our last talk, which is Franz Franchetti, who's going to talk about how we're going to eliminate the fixed list of sizes problem in library in the current deployment strategy. So Franz.
All right, thank you, Phil. All right, so yeah, I'm going to be talking about just-in-time compilation or runtime compilation as a part of the strategy. And so let me start out first with a question. If you have ever wondered about this peculiar thing that in the linear algebra space, we have LAPACK, scale LAPACK, and then we have the BLAS underneath. And that together gives a nice layering that allows us to get performance across machines. And that has been around for quite a while and been very successful. In the spectral algorithm domain, in the FFT space, we have something like FFTW in the bottom, but all the higher level algorithms, everybody is writing by hand based on that lower level. So there is no equivalent of LAPACK or scale APAC here. And part of there are a number of reasons, but one of the biggest reasons for that is what Phil was saying at the very beginning of the tutorial, which is there's so little low arithmetic intensity that doing a decomposition where you reduce it to a smaller problem would incur O of n overhead of copying that would be totally destroying the performance. And so that's why going to a view where you have a top-level spectral pack and a lower-level FFTX is a challenging question if you want to do it only with libraries. Now, code generation and the optimization that we're doing gets us there because we can then, for every particular case, do all the complicated optimizations in one shot. But that, if you don't be careful about it, the interface gets very, very complicated at that point. And so what we're faced with is we want to have a very nice interface for users that looks like a library, but behind the scenes, we would like to have code generation that leverages all the little things to get a high performance. And we cannot invoke a external compiler at runtime because we're on a supercomputer where that is not possible. So runtime compilation comes in here to solve that otherwise unsolvable problem for us. And to give you a little bit more idea of how that looks like is we're here back to that free space algorithm that there was some discussion in the chat before. And so if I draw it out just as a couple of boxes, you see I have a small blue box. I have to zero pad it. Here it's more than a factor of 2. Then I have to FFT it. Then I have to multiply with some kind of symbol in the frequency domain that has some kind of symmetries that's seeded from a smaller cube. And then after I'm done with that, I inverse FFT, and then I throw away the good part and only keep the upper right yellow box of it. And that's then a particular Hockney convolution that Brian and Phil and Peter can talk a lot about it. But for me, it's just, see, you have size 33, you have size 65, you have size 130, and you have weird symmetries. So you have to really know all these numbers in order to perform the full optimizations. If you try to do them beforehand, you get such a combinatorial explosion that there's just nothing you can do. Now, beforehand, we get back to the slide that Phil was showing at the beginning of the tutorial. That's how we would like to define it. We'd like to have some nice high-level C++ code. We put the limiters in red that say from here to here is the computation. We have a definition of the computation, and we have an invocation of the computation. And behind the scenes, the system produces for exactly the particular case that we're executing the high performance implementation. And so we get exactly the kind of interface the application people would like. We hide the platform, we hide the code gen. It looks like a sequence of library calls, and it gives you really write once, run anywhere, and automatic performance tuning and performance portability. Now, here is the thing. When you write a thing like that, then you have to make very sure that you write the application that as a specification, not as a program. You have to forget the idea of writing the library and doing little performance optimizations yourself, because the automatic system is going to do the performance optimizations for you. So you really are writing a specification that's dressed up as a program. It needs to be clean and concise, no low-level tricks. Think performance. Don't think performance, think correctness. Make sure it's as simple to understand and as clean as possible. And you define the semantics of a new library object here that is going to be built from a sequence of library calls. So that's basically what's really happening when we write FFTX C++ code. We're writing a specification. And then behind the scenes, that specification is going to be turned into a specification in the Spiral internal language that gives you a little bit of a flavor of what it is. It describes in the Spiral underlying computer algebra system the geometry of the distribution Semeng talked about, the calculation, the zero padding, and all of that. And that then goes into the Spiral code generation. And at that point, you have the full specification, including all the data layouts, all the problem sizes, everything that you can do aggressive optimization. Now, that captures the entire computation across multiple library calls. It may contain user-defined callbacks. It captures the pruning and zero padding that Andrew is talking about. It captures symmetries in the symbol, and it lifts a sequence of C++ library calls into a specification, an abstract specification that's really math in nature. And that is the necessary entry point for the code generation. And to give you an idea of how complex that can be, this is a snippet out of how the warp-X applications convolution is being declared. And you see, I need to write a page of computer algebra code to define all the different variants of how the data gets resampled and shifted around and convolved. And then the middle pink part is the actual callback function, which requires another page of computer algebra system code to describe exactly how the symbol in the convolution gets computed from a lot of seed tables and whatnot. So all of that is information that the code generation system at runtime, only at runtime has, because these things depend on the exact application you're running, the problem sizes, and whatnot. So what happens now is that the moment the system sees the entire specification, historically, it would produce for one size, one file that implements that size at high efficiency. And how does it do it? Well, it first goes in and analyzes the input and sees whether it finds a pattern to lift it up to a higher level object. And that is really looking at the computation specification and translating it into a pattern that the spectral pack, the higher level red part that I showed you at the beginning, basically does. And then it's going to take this high level operation and break it down in ways that the user didn't even think about by combining three rule sets. A rule set that captures hardware properties, that's the red one. A rule set that captures compiler transformations and loop transformations, that's the gray one. And a rule set that captures actual computation and algorithm rules depending on the problem size. And that together spans a search space. And then a constraint solving system walks through that search space, finds solutions that implement the algorithm at that particular situation, and then sends it in the write to the stack of multiple rewrite systems that implement either a recursive descent or confluent term rewriting. And at the very end, you get a library file implementing a particular instance of the problem, pulling all the optimizations known to the system that we have seeded over the last 20 years by reading plenty of journal papers, reading Brian's PhD thesis and whatnot. Now that has to be done for every particular instance. And so we now have to do that at runtime when we know the thing end to end. Now, the other thing that Peter was briefly talking about is that, of course, we have to do performance engineering on the way because we want to get best performance. And the philosophy in Spiral is to perform the performance engineering at the highest abstraction level possible. So there's some aspects where new algorithms have to be actually found as the new hardware comes in. Then known program transformations have to be adapted in situations that they were not meant to be beforehand. Then loop transformations, code transformations, regularizations, whatnot has to be done. Anything from algorithm level down to pretty printing and lowest level machine configuration things. And after all of that is done, you have for a particular machine, a particular problem, and a particular application scenario, the code. And so again, that shows you why preceding it with all the potential cases only works when you have applications that have a very specific set of use cases that are worth it. But if you want to deploy it as a library, you have to do that at runtime. Now, what does it mean to do that at runtime? What it means is you're given with a high-level specification and a set of algorithms and breakdown rules and whatnot, and you have to mathematically compile those into a library that at runtime can be stitched together to execute for the particular use case at very high performance. Now, there are three ways of how one can do that. The first way is that we have looked historically, that we're doing right now, which is, well, you talk to the application people, you make an educated guess, and you run that offline for all the sizes that you can think of. And if you run into a situation where there is a size that you didn't think of, you just have to go back and rerun a part of the seeding. So that is the collection of sizes. And in a particular supercomputing space, that might work pretty well. But in general deployment, that doesn't quite work. So that we have to go beyond. The next one is to build basically something like FFTW from that specification. That's prior work that Yevgen Voronenko, part of the Spiral team, has done as early as 2008 in his PhD thesis. That works very well as long as the computations that you're trying to do are limited. So you can do FFTW for FFTs, but building FFTW style library for the context of entire FFTX turns out to be very hard. And so this is really more a fallback solution. And the last solution is to say, well, we have a system that can produce extremely high performance code for a particular instance. So why don't we just stick that into a just-in-time compiler or a runtime compiler? And that's what we are also pursuing, in part in collaboration with an X-Stack project, Bluestone, with Jeff Vedder, and with other projects we're doing. But we believe that that approach in the general sense here for FFTX in ECP is the right approach. Now, since runtime compilation can take a while, using lots of caching and lots of pre-evaluation from 1 and 2 and combining 1 and 2 into 3 partially might be the proper engineering approach in the long run. Now, how does this look like? You have on the left side the executable. You have the C++ code, and then you have the definition side of FFTX and the call side of FFTX. The definition side and the call side of FFTX talk behind the scenes to Spiral that has all, the entire code generator and everything with it. And it's pre-seeded codelets. It might stitch together codelets, or it might invoke the actual entire runtime compilation stack, depending on whether you're running on a CPU, you're running on a GPU, how the software stack for the particular target, how well it's developed, and how much you can pre-build at deployment time because you know the applications and you know the problem sizes. In the worst case, if it's a thing that FFTX has seen the first time ever, it will have to run the entire runtime compilation thing right there. If it's things that show up time and again, the equivalent of FFTW wisdom is invoked, and we will cache partial results on the way wherever we are. Now, technically, it looks pretty simple. Instead of writing the left side, which is a .cu file, to a file, compiling it and linking it in the way Patrick was demonstrating it in the first part of the tutorial, we just put quotation marks around the entire thing. and sticking it into the runtime compiler, and then getting back a function pointer we can call. So that's at the highest level. It's a very simple transformation that, depending on how exactly the runtime compilation system works, maybe there is a little bit of extra interpretation or a little bit of extra infrastructure necessary, shown here in the middle part on the right side, or maybe one can just compile the entire file by a combination of LLVM and accelerator compiler. That's what we are working on in the next phase of our project here. And just to put that into bigger context, this is really part of a bigger ecosystem where we are working on the Spiral system to plug Spiral into compilers and to make Spiral the engine behind the entire host of such code generation powered libraries. On the upper left, this is really a multi-language, multi-target infrastructure where we're looking C++, Python, but also MATLAB and potentially Julia and others as input. And the output can be CPU, FPGA, GPU, but we're even fabbing accelerator chips with RISC-V in that space. They're using well-known abstractions like FFTX, FFTW, LAPACK, and whatnot as domain-specific language to glue it together. This is an instance of cross-motive optimization where we are leveraging Phil's earlier work on what are the motifs used in scientific computing in order to have multiple of them interact, say linear algebra and FFTs, and then do cross-library, cross-motive optimization. And WarpX is one of these examples where this has to happen. And there are two deployment modes. One is the Snow White system that is was developed in DARPA Papa and now is worked on in the XStack Bluestone project, where we really plug that entire thing into the LLVM compiler via MLIR and LLVMIR. And the other one is a active library, LibraryX approach, where FFTX is an instance of, but there is also GraphPlus, GPTLX, and number theoretic transform, crypto, NTTX, and many other ideas where we are trying to use that. And that's the active library infrastructure we're doing here. So you see what we're doing in FFTX leverages the work of Spiral and brings it to the next level, while at the same time giving us a next generation open source FFT library in the ECP space. Thank you. And back to you, Phil.
Okay. I think before we open it up to questions, which I'd like to, I would like to just share one slide, which kind of summarizes what our deployment schedule looks like. So let me see if I can do that. Share screen. Let's put this up here. Come on. No, let's go away. That's not what I wanted to share. Okay, now we'll share screen. All right. So let me do this as a slideshow. All right. So this is, there are lots of moving parts here, right? We have single device FFTs, distributed FFTs, and then 3 integrated algorithms applications, plus a question about, okay, how are we going to support things like Hefty and the COPA solvers, where they have a distributed framework for their FFTs, but it depends on having a single device FFT as a backend. But it's a different requirement because they really need to be able to specify at a fairly late binding at the time their user invokes a Hefty library call, the single device FFT size. So what we have done here is for single device FFTs, we've done a baseline implementation, performance engineering. We've done the fixed list library, and those are things that are available. The fixed list library is really what you would get when you download and try out FFTX, as Patrick described in his talk. Now, so going forward, by the end of this fiscal year, by the 1st of October, we expect to have at least a first pass on SYCL for single device FFT, And then there's this question of, okay, are we going to use FFTW style codelets or full JIT? That's a question, the answer to which has been evolving rapidly. And it's mainly because what we are hearing from the vendors is that their runtime compilation tools are sufficiently mature that we can try using them here as well. In any case, that's what we're going to try to decide over the next 4 months and make a down select to whether we do codelets or runtime compilation. I will just note that we heard from Malcolm Roberts from the AMD team, Math Libraries team, earlier this week, and they mentioned that they are looking. They're also doing a code generation framework in Python, and they are looking to deploy that using the AMD runtime compilation tools. So that's another data point, and I hope we will be able to continue to talk to them. But I think that the runtime compilation tools, certainly for NVIDIA, certainly for AMD, are fairly mature, and we need to make an evaluation. Our goal is to make an evaluation in the context, okay, let's see how we would deploy single device FFT. Now, we expect to get fixed list libraries for everything else by the end of September. The one exception is Hefty and the solver, the larger scale distributed libraries. And the reason is we really cannot provide them what they need without being able to specify, okay, a user comes in at runtime and they say, I want this size FFT with this distribution. We need to provide the device level FFTs at the appropriate sizes and have them be specified at runtime, which that means that we need to decide on one of these or the other and deploy them. That's the point at which we will deploy with Hefty and Copa. We know what else we need. We know what the library interfaces need. We did the scoping study, but part of the scoping study, the answer was we can't use fixed list libraries. So that's on our list as well. And then once we've made decisions on which style of runtime compilation or codelets we're going to use, then over the course of the next year, we'll be building out more of the infrastructure. We'll be building out runtime, either runtime compilation or codelets for distributed, for these applications, and for library support. So that's what I wanted to say about that. And we have a bunch of questions down here, so let me look. Okay. And yes, and Malcolm has just confirmed in the chat window, we will be using C++ for runtime compilation in Rock FFT, and that's what he told us. And I am looking forward to discussing that in more detail with him. Oh, you're using, I'm sorry, not Python. Okay. So actually now kind of your workflow structurally is looking even more like ours, because that's what we do. We have C++ as the front end, and then we're calling Spiral as a DLL. That's our plan. Okay, good. Any other? So now I'd really like to open it up for questions.
Phil, if I may ask, are there any thoughts on actually providing something like FFTW wisdom, which can actually inform the user as to the best backend that they could make use of on a platform?
Ooh. Yeah, so which backend meaning?
So for example, if you have something like Aurora, is it advantageous for them to actually use the SYCL backend or the OpenMP with offload backend for their specific problem?
I don't know. Semeng, do you have an answer to that? My short answer is I don't know. I'm not even sure what that.
At this point, no.
Okay.
It is an interesting problem, but that's not something that we have looked at. We've looked at them individually as opposed to across all of them. Franz, what do you?
I just want to say that there are two aspects of wisdom, right? There's the one question of does it know what's the right architecture? And that's kind of like an auto tuning. And we haven't really done auto tuning quite yet. But as we get to auto tuning, it will be a natural thing to try out all the different backends and then go with the one. This is purely speculative, but usually what we do. The other thing is that there is the wisdom of what's the right algorithm decomposition and not to have to redo all the search and all of that. And as we are building the runtime compilation out, we will be caching partial results everywhere down the stack because we will want to make the runtime compilation time to solution as quick as possible. And so that kind of wisdom will surely creep in. It will be way more distributed and multi-level than FFTW does it. And the other one, once we get to auto tuning, it will naturally come in, I expect. The timeline of it, I wouldn't know. Looks like Brian also has something to add.
Yeah, I mean, we build up wisdom in Spiral in the breakdown rules, right? The breakdown rules in Spiral are an expert system that is ever growing. And that's okay. Like we can spend a lot of compute effort there, and the search, everything you want to do is actually to constrain the search and find smaller spaces to sample the auto tune. But my suspicion is that for Aurora, we will bind to the lowest level, which is the OpenCL, and rely on the fact that SYCL supports OpenCL kernels, and the OpenMP offload is promised to support OpenCL launch kernels. Going the other direction is harder. So I think we'll end up generating, we'll code gen down to OpenCL and runtime compile it. OpenCL has been a JIT world since the beginning. So they got there first, and then no one wanted to program it because it's too hard. So we're going to program it for you. So I'm actually pretty confident that we'll have, JIT compile time, full reconfigurability on Aurora before the rest of the platforms is really bulletproof.
Okay. Any other questions? We're almost out of time here. So someone has one final burning question they'd like to raise. All right. Well, I'd like to thank everyone for coming, and we're all we can be reached on the chat window on the Slack channel for ECP. I'm there, and most of the rest of the team is there. I would also, we still have openings for engaging with other applications, and I would encourage you, if you have an applications for which FFTs are kind of a critical performance bottleneck, to talk to us and let us know what's going on. All right, good. So I think we can adjourn.
Okay, I'm stopping the recording.
Stop. Thanks, guys.